Let's take a look at this challenge. The target application includes a web page and I'm using a very user-friendly database client that supports drivers for many databases. The backend of this challenge is a Java-based application which uses JDBC Java Database Connectivity drivers. Typically, JDBC drivers are maintained by the respective database vendors to enable connectivity from Java applications. Building a database client in Java is quite convenient. You just need to load the appropriate JDBC driver. However, JDBC can also introduce security issues. For example, older versions of MySQL are vulnerable to deserialization attacks. PostgreSQL poses an even greater risk. It can invoke no-argument methods on arbitrary classes via reflection specifically. It may instantiate and execute Java classes like call4XML to perform remote XML loading. Additionally, certain classes support JNDI lookups, which can also be exploited. The key to solving this challenge lies in DuckDB. Since the entire environment is air-gapped, no outbound network access, we must rely on capabilities that work entirely offline. DuckDB fits this requirement. It can be instantiated locally and supports several advanced features, including plugin extensions, which are a core part of its functionality. DuckDB classifies extensions into three categories based on code signing: officially signed extensions. These are signed with a private key held only by the core team. Unless you obtain that private key, which isn't feasible, you can't create valid signed extensions. Distributed extensions. These are delivered through official channels, but again, not accessible to attackers in the short term. Unsigned extensions. Users can write and load their own custom extensions. Importantly, some community-provided extensions contain high-severity vulnerabilities. One such example is Shelfs, a community extension that enables command execution through file system operations. By default, DuckDB allows loading community extensions, though this can be disabled via configuration. Moreover, DuckDB supports binary data types and allows writing binary content directly to the FIRES rack, provided you have sufficient permissions. This means we can write our malicious extension, either Shelfs or a custom one, directly onto disk. In my case, I created a simple custom plugin that executes the find command to locate the flag file and outputs its contents. However, in practice, the quickest approach during a CTF is to use the existing Shelfs extension. Just run a command to find and print the flag. This design intentionally avoids unintended solutions. Otherwise, players might simply read the flag directly or escalate privileges via a SUID binary to achieve command execution. The end result is similar either way. Identifying SUID binaries is straightforward. You can easily list which programs have the SUID bit set using this logic. We can successfully exploit the challenge. Additionally, while reviewing the source code, I discovered that the BIF module in the application allows anonymous file uploads. Uploaded files are stored in a temp directory, and the server enforces that the uploaded file name must be a valid UUID. If the FileName parameter isn't a properly formatted UUID, the server throws an exception. I leveraged this by uploading my custom extension with a valid UUID file name, then triggered its execution via a script and successfully retrieved the flag. This completes the full exploitation chain for the challenge.